Hello, everyone. This is Nejjar from Bonn University. And first of all, I would like to thank the organizers of the GPSD for giving me the opportunity to give this talk. And I would like to thank you for watching this video. So I will be speaking about the cutoff profile of the asymmetric simple exclusion process on a segment. And this is joint work with Alexei Bufetov from Leipzig University. So I will start by introducing the model. So ASEP on the segment means that there are k particles placed on the integers from 1 to n. So in this illustration here, we have 4 particles. And what particles do is that each particle waits an exponential time, after which it tosses a coin, which is telling the particle whether or not it should try to make a unit step to the right or to the left. And the probability that the particle will try to jump to the right is p, and p is strictly bigger than 1/2, meaning that particles have a drift to the right. The interaction between particles comes to the so-called exclusion constraint. So this constraint is that a particle cannot jump to a side that is occupied by another particle. So in this illustration here, this particle can jump neither to the right nor to the left, whereas this particle here can jump to the right, but not to the left. This particle here can jump to the left, but not to the right, whereas this particle here can jump both to the right and to the left. So this defines on a continuous time Markov chain with finite state space, and we can write down the state space omega in k as consisting of all configurations xi and 0, 1 to the n, such that the entries of the xi sum up to k. And this model ASEP was initially introduced in biology to model proteins. It can also be reformulated as an interface model, as a growth model, and as such, it belongs to a large class of models which form the so-called Kardar-Parisi-Zhang or KPZ universality class. And as will also appear in this talk, ASEP is closely related to random matrix theory, to combinatorics, and to algebra. So what we will be concerned with is the mixing of ASEP on omega and k, so on the segment. So what is easy to see is that ASEP has a unique stationary measure pi and k. And if you recall that particles have a drift to the right, it is clear that under the stationary measure pi, particles will have a tendency to be to the right of the segment. For example, if p equals 1, then the stationary measure pi and k is just a Dirac measure, which is concentrated on the configuration where the k particles are as much to the right as possible. So we will look at the ASEP xi t, which is the ASEP started from a certain initial configuration xi from our state space. And we will denote by pt xi the law of the configuration xi t. And what we want to study is the distance between the law of the process at time t and the stationary measure pi and k. And in order to measure this distance, we use the total variation distance. So we define a function d and k of xi, which at time t is equal to the total variation distance between the law of the process at time t and the stationary measure pi and k. Okay, and here, just as a reminder, I've written down the definition of the total variation distance. So what follows from general Markov chain theory is that d and k of xi converges to 0 if we send t to infinity. So what we will be looking at is the worst case total variation distance d and k, which is defined from the d and k xi's just by maximizing of all initial configurations xi. So this is the worst you could do in terms of distance to the equilibrium measure. So you look at the psi for which you are as far as equilibrium as possible. And in particular, if you know that this function dnk is small at time t, then you know that regardless from where your chain started, you are close to equilibrium. And our main result gives the behavior of dnk as time and nk go to infinity simultaneously. So here's our result. So we do assume that that there's a positive density of particles. Otherwise, it's easy to see that the result is not true. So we assume that the number of particles kn divided by n converges to a constant alpha between 0 and 1. And then our result says that for a parameter S in R, we look at the total variation distance dnkn, and we look at this distance at a certain time point. Namely, there's a macroscopic time point which is written in red, and that is given by the square root of k plus the square root of n minus k. And this red term here will be of order n. And around this macroscopic time point, we use our parameter S to let time vary on the scale n to the power 1/3. And then we divide everything by the strength of the asymmetry. And the result says that if we rescale time in such a way, then the total variation distance will converge to 1 minus FGV of S times a constant factor f of alpha, which solely depends on alpha. Okay, so what does this result mean? So first of all, what is this FGV? Well, this FGV, first of all, it's a probability distribution function. So in particular, if you send S to plus infinity, this right-hand side here will converge to 0. And if you send S to minus infinity, it will converge to 1. And this FGV is the Tracy-Witten distribution, which originated in random matrix theory. But it also appears as limit law of rescale particle positions if you look at ASEP on the whole integer lattice. For a certain initial configuration, you get FGV as limit law. Okay, so let me now rephrase this result in the language of Markov chains. So what the result is in particular telling you as a very simple corollary is that if you look at the total variation distance on the scale n, then this distance drops from 0 to 1 abruptly. Namely, if you look at the total variation distance at the time point n times the square root of alpha plus square root of 1 minus alpha, and then you multiply that by your parameter S here, then this will converge to either 1 if S is smaller than 1, or to 0 if S is bigger than 1. And this abrupt convergence means that ASEP exhibits the so-called cutoff phenomenon, which was by a rather different proof already shown by Labie and Lacroix. However, our result goes beyond that. Namely, what our result is telling you is that this transition from 1 to 0 of the total variation distance is smooth on the scale n to the power 1/3, which in the language of Markov chains means that the cutoff window of ASEP is n to the power 1/3. And since we also explicitly compute the limit, we also obtain the so-called cutoff profile of ASEP, which is given by 1 minus FGV. Okay, so here I'd like to stop and I'd like to thank you for your attention.